Welcome back, everyone. In this math page, we're going to be looking at vector addition and resolution. A resultant, remember, is when you add two vectors, and whatever you get from the sum of those vectors is your resultant. Now, in the concept page today, we're looking at anything at an angle. So two things like an east and a west, you're not going to have a resultant that's east or west. It's going to be somewhere in between, and it follows the parallelogram rule. This is really simple because all we're doing is we are either adding with a force or subtracting from a force because the force is directly opposed to us at no angle. Okay, so this would be like two people arm wrestling, one going east, one going west, or whatever you can imagine where one is directly opposing the other. So here's an example. A small rubber band powered airplane can fly at 2.5 meters in still air. Okay, so let's imagine that it's flying this way. This would go, its vector, its magnitude is 2.5 meters per second. Okay, that's the scalar portion. And this would be the direction that it's going. Now, it doesn't tell us what direction it is, but whatever direction that is, okay, is in a direction. And so we can either add with a direction or cancel it if it's opposing it. Okay, so let's look. If it flies into a headwind, now headwind is air that's coming directly at you. All right, so the headwind in this case is coming directly at you, and it's going to cancel either all or part of the 2.5 depending on how much it is. It says that this is a half meter per second headwind. So I've got a half meter per second going this way. You can see that to the left I'm going to have a stronger force than to the right. Okay, smaller force than to the right. Okay, so what are we asked to do? It says, what is the speed relative to the ground? It's not really asking us which direction is it going to fly. Let's imagine that I'm starting to fly it going this direction, okay, to the east, whatever. We just set it a direction. And the headwind is directly opposing it, so we'll have this going to the west. It's not saying what direction is it going to end up. See, I can kind of figure that if I push 2.5 to the right and 0.5 to the left, oh, I've got this wrong. This is not 5, it's 0.5. So this is a lot bigger. So it's going to keep going to the right. The 0.5 is only going to eat up a little bit. Okay, sorry about that. I'm a little stupid. So I've got 2.5. That's a lot bigger. That's $2.50, and this is 50 cents. Okay, so I'm going to end up with $2 going to the right. 50 cents is going to eat away 50 cents here. You can see I always relate everything to money when I see it. So what are you going to do? Math-wise, you're going to have to set a positive with a certain direction and a negative with its opposite. So I don't care what we set. Let's just set the two in a, let's say in this particular problem, to the right is positive and to the left is exactly opposite. We'll make it negative. So you're just going to add them together algebraically. You're going to have 2.5 positive meters per second and then add a negative 0.5 meters per second. So you're adding these two. One is a negative term, one's a positive term. So it's going to eat away. So when you take a 2.5 and add a negative 0.5, you're going to end up with a 2 meters per second. Now we know that it's still going to the right because you had leftover force here. But the question didn't really ask that. It just said relative to the ground, how much is it going? See, 2.5 was still air, but it's not in still air, so I'm actually getting opposed by some of the wind. It's going to eat away some of my power. So it's the same going to be going forward, but it's going to be going forward slower than if it were in still air. Okay. The second question, what is its speed in a tailwind with the same magnitude? Now, a tailwind is pushing you from the back. So it would be the exactly same. I'm just going to set this up again, 2.5 meters per second going to the east. But a tailwind, I can either add it here or here. I'll put it in the tail since it's pushing. And so this is 0.5. That means that these two are going to go in the same direction. So they're both going to be positive. So when I add them together, they're not going to oppose each other. They're going to add together. and you're going to get 2.5 plus 0.5 equals 3. So 3 meters per second. So if someone's standing on the ground, that plane would be going 3 meters per second flying. But if it had a headwind coming at it, it would only go 2 meters per second. All right, I hope that helped you. So let's look at a couple of these examples. A stream flows with a speed of 3 meters relative to the shore. All right, so I don't know, let's draw a picture. Okay, I've got a stream. Here's my stream, and it's going 3 meters per second. Let's just say down. Okay, here's me. I'm standing here looking. Okay, and it's heading this way. So I guess to me it's going left. And it says a kayaker paddles downstream. So his kayak. Okay, here's his kayak. He's going downstream, and he had relative to the stream is going 1.5 meters per second. So he's actually going faster than the stream. See, if according to the stream, if he was looking at the stream and he wasn't moving, like I could see him moving, but if he was looking at the water and he wasn't moving in the water, he would be going exactly the same. He would be going 0, but yet his 0 is being carried away by that river, and so he's actually going 3. He's going 1.5 relative to the stream. That means he's going 1.5 faster than the stream is moving. So if he's going 1.5 meters per second down, he's going downstream, then I'm going to add these two together. They're both in the same direction, so I'm going to set them as both positive. So I've got 3 plus 1.5 meters per second. So I've got 4.5 meters per second relative to me, who's watching this happen on the shore. To me, I guess he's going left, but according to what we're seeing, he's going down. We're just setting them. We just want to know, are they in the same direction or are they opposing each other? Last one, a train travels with a speed of 25 relative to the ground. Okay, so here's my my train. Okay, my train. I don't know what a train looks like. I think it's like this, and there's a choo-choo on the top, something like that. Okay, there's my train. And I'm on the train. Okay, so here's the windows of the train. So I'm on the train, and it's going 25 meters this way. 25 meters per second. If you walk to the back of the train, so I'm actually walking to the back of the train, it's going very fast this direction, and I'm going very slow in this direction. So do you see, relative to the guy on the land, I'm going forward. Relative to the people inside the train, I'm walking to the back. All right, so you have to say, where's your frame of reference? I'm going this way. So if my train is going 25 to the right, I'm going to the left. So I'm going to set my rate as a negative number because I'm opposing the other one. Okay, I'm at 0.5, and I'm going to add these two together and see what my speed is. Now, it's not really asking the direction. I'll tell you that my direction is still going to the right, but they just asked my speed. So I'm going to eat away 50 cents out of my $25, and I'm going to get 2450 meters per second, or 24.5 meters per second. And they didn't ask, but it's going to be going in the same direction as the train. The train is moving forward fast, and I'm moving back a little bit, and I'm eating away some of the speed that someone would, if they were only looking at me, how fast am I going forward? The same as the train? No, I'm actually slowing down because I'm moving to the rear of the train, so I'm not moving forward as fast as the train is. So everything is relative to where you are, your frame of reference. Okay, keep working.